We start with proximal convoluted tubule. So from this slide, I want you to see what I wrote on the board. They're your most active reabsorbers. If you look at a little cut tube of PCT and compare it to DCT, the cells are larger. They have more mitochondria. They have they're a simple cuboidal ET with a microvilli brush border. The cells are more active. They do more work. DCT are also a simple cuboidal ET. They're not as active. They don't have as many mitochondria. There's no brush board. They're not as active. In this slide, I want you to see that the main function of these cells is reabsorption. They do secretion as well. We'll focus on reabsorption. The idea of reabsorption is you remove something from the filtrate and you put it into the blood. And to use this ferry analogy, imagine you're transporting glucose out of the filtrate to resorb it into the bloodstream. Let's say that your blood glucose level is within the normal range. Just give you a number here. And if there's not too much glucose being filtered, the PCT should be able to handle 100% of the load. However, in hyperglycemia, if there's high blood glucose and it all gets filtered, the PCT can't handle everything. There's not enough of these orange transporters to ferry it all back. So, some would spill into the urine. So I guess what we learned is the function of reabsorption and secretion, they have these rate limits. They have rate limits. They have transport maximums. You can max these little molecules out that transport the things you want to reabsorb or secrete. And so appreciate that to move something from the filtrate, yellow fluid, to the bloodstream, you have to get it through all of these places. From the filtrate, the main things you move it through is number 2 and 3. The luminal membrane, the side that faces the filtrate, or the lumen of the tubule, and the side opposite, the basal lateral. Then you have to get it through the interstitium and finally through the capillary wall. We're going to focus on 2 and 3. How do you reabsorb past those cellular barriers? And to teach you the physiology of the PCT, I'm going to focus on just one thing. There's so many things you could talk about, but I feel if you focus on one thing, all the other things kind of fall into line. And that is the reabsorption of sodium. And if you just look at the numbers, you filter a lot, okay? 25,000 millimolar. So if that's our 100%, 25,000 right there. By the time you get to the end of the PCT, you've reabsorbed 2/3. So you've reabsorbed most of the sodium in the PCT. That's why I'm going to focus on it. You get all the way through the end of the nephron, you barely have 100 of the 25,000 remaining. So nephrons are very effective at reabsorbing sodium. It's a much needed electrolyte for the body. Now to understand how the PCT cells do it so well, understand one thing. Between PCT cells, they're stapled together. These are tight junctions. You write that down. That's important to know. Things aren't just going to seep through. Well, things can get through there, but not very many things. We're going to focus on the things that go through the cell. We call that the transcellular route. So I'll say items don't slip in between cells. Things must go through the cell. To be reabsorbed. Books call that the transcellular route. That's what we're going to focus on. In other words, call it the transcellular. So I have a picture of a cell here, and I have some numbers here. Let me talk about the numbers I have on this slide there. I have some numbers in the cell. -70. And 15 millimolar. This is referring to sodium concentration. So that's in the cell. On one side of the cell, on the filtrate side, it goes, well, you can see it, -3, 145. Okay, consider you're a sodium ion. And you're passing by, you're in the filtrate. You know, sodium is a ion that carries a full positive charge. So sodium ions are very small, but they carry a full positive charge. And look at your concentration in the filtrate versus in the cell. Pretty much this gradient favors entry into the cell past this luminal membrane. Typically things flow from high to low. So as long as there's a transporter for sodium, it could probably just go through there without the usage of ATP. Now also consider a positively charged ion. Here's your electronegativity of the filtrate. It's much more negative inside the cell. That also favors entry into the cell. If you're positive, you're attracted towards more negative. So what we say is the electrochemical gradient favors sodium entry past this membrane. So I'm writing electrochemical gradient favors entry. We call that on the slide, it's downhill to that membrane. Requires no energy, no expenditure of ATP. Like we roll a boulder downhill, you don't have to push it, it just rolls by itself. Okay, and the same thing for the other side. Here's the lateral. Well, you can just say the reverse things. Well, look at the numbers. What is it, 0, 145? Well, now let's pretend you're in the cell. and you want to move past the other membrane. Well, you have to go against both gradients. It's like, well, you're going from less positive, or you're going from more negative to more positive, and you're going against the concentration gradient, so that's uphill. So if you do have to move sodium across this membrane as well, and it's going to be uphill. You do have to expend energy. So uphill, downhill, it's easy to understand, I think, if you just kind of look at the numbers and think about it just for a second. All right, so uphill, downhill. So that's what you have to do. You have to kind of like, think about, how do you accomplish uphill, downhill? You do need transporters. Okay, so look where I'm pointing. I'm pointing to one little purple dot right there. That's the one we want to start with. So of all the busyness of this slide, and we want to talk about how these cells reabsorb. Well, one thing we learn is PCT cells reabsorb effectively by creating a negative intracellular environment. So I put negative exclamation point right here. One thing, if you create a negative environment, it's like you want to draw positive sodium into you. That helps. Another thing is, if you keep, second thing, not only are you negative, as I say on the slide, you keep this number low. You keep sodium low. Sodium from the outside wants to enter the cell. So both of those things are going to favor reabsorption. And so I'm going to erase some of these notes here and talk about steps here. Now there's a lot of steps here, and there's a lot of busyness. Again, I'm just going to focus on the reabsorption of sodium, and everything else falls into place. So, all right, let's pay attention to number one. This is the basilar membrane, and just focus on that one molecule, reabsorption of sodium. That is the sodium-potassium ATPase pump. You studied that before. In resting membrane potential for the neuron, it makes the inside of the cell negative with respect to the outside. It's negative 70. It's the membrane potential, and we see it here again. Now start paying attention to the arrows. Okay. For example. If you see solid arrows, in this figure it means active transport. Okay. Transport meaning, the molecule can't just flow past the cell membrane freely. It does need a transporter, the protein molecule. And you do need to expend ATP. That's what active means in biology. Use your money, your currency, your ATP, your energy for the cell. Let's see. If molecules are being transported XY, as an example, in opposite directions, sometimes the word that's used is countertransport versus co-transport. But if you were to, transport them both in the same direction, that would be called co-transport. However, if you have dotted lines, for X and Y, it's co-transport, but it's not active, it's passive. No, I'm sorry, it's not passive, it's secondary active transport. So, solid lines is active transport, primary active transport. Let's say this one, primary active transport. Let's say this one here, dotted lines, secondary active transport. This one there versus this one there. The only difference is one is counter-transport and this one is co-transport. Okay? And these are the two examples that we're going to focus on. You do have passive transport, but I'm not going to focus on that for this figure. So, I mean, that's the terminology. You should remember primary active transport uses ATP, secondary active transport does not. I remember that was on my first test in 430. I'm sure it was mentioned in other classes. So the number one is on the figure. That's transporting sodium in one way, potassium in the other way. However, notice that the potassium, it's pumped in, but see how it leaks back out? So, by pumping out the sodium, pumping in potassium, which is positive, but then the positive potassium leaks back out, that is creating a negative intracellular environment. So this molecule pump out sodium. I believe your book used to call it the sodium exodus. I don't know what it still calls it, but anyways, you're pumping out the sodium. And then positive potassium leaks back out. So that accomplishes our number one, number two things. You pump out a positive ion, the positive ion you pump in leaks back out. Both of these things create your negative 70. Also, you're pumping out sodium, so sodium levels are low. So both of these things is what I'm kind of getting to. Now you have this downhill situation on the other side. So if you pay attention to the luminal membrane on the other side, that molecule, maybe this one here, it's a sodium co-transporter, luminal side. I should have wrote luminal on that side. So there's no confusion. Luminal is this side. I'm just writing on the wrong side of the white board. So let's label this primary. So this primary. And what I mean by that is primary active transport. You have to expend ATP to do this. Cells are very finicky about using their ATP, so you know it's really important. Okay, so the luminal membrane, you've got this molecule here, it's a secondary active transporter. It's a sodium something co-transporter. Let's say, for example, it's glucose. Could be anything. On the figure, it says it's sodium, but it could also be glucose, amino acids, ions, vitamins, other things that you want to conserve and not lose to the urine. Okay. So anyways, it's co-transport. It's secondary active transporter. So basically, sodium has got a free ride. It can just slip on in. Because it's secondary active transport, it uses the concentration gradient established by the primary active transporter. Sodium can use the electrochemical gradient established by the primary active transporter. It's doing the pumping, the hard work of using ATP, pumping. Primary active transporter. So in secondary active transport, no ATP is used, but you're benefiting from the work of the primary one. Now, the thing is, take something along with it. Something gets a free, something kind of piggybacks on sodium, just goes along with it. For example, glucose. Same thing that's a glucose or something else that's inside the cell. Glucose just goes along. It kind of rides the wave of sodium being taken in by its transporter. It just gets a free ride with it. Glucose goes along with sodium. It's co-transport. They both go together. So the molecule has to accommodate both molecules. They have to fit. But the point is, glucose may be going against its concentration gradient. It doesn't matter. You don't need energy to get the glucose across the membranes. Is benefiting from the energy that sodium can travel down. Okay. It's kind of like when seaweed washes on the beach. Is seaweed following a concentration gradient? No, it's the energy of the waves just washing it ashore. Okay, it's kind of like glucose is being washed into the cell with the sodium, and this is kind of how these cells are the most active reabsorbers, this idea of co-transport. Just work hard to get it so you can reabsorb one thing, just take other things with it. And that's all I'll focus on for this figure. They do talk about some other things I may mention later on. For now, let's kind of keep that straight in your head. So just study those two molecules, this one and this one. So I'm going to move on, but if there are any questions on that part of the reabsorption story. Yeah? On the luminal side? This is the luminal side. Oh, yeah, you're right. I should stick to the key. It's because it's a secondary active transporter. They use dotted lines, and so should I. I forgot. And then same thing for this one. So we'll stick with the dotted lines there. I did use blue for glucose, just to symbolize it's a different molecule. But it's a secondary ion transport. Any other questions? Okay, true, false. This molecule utilizes ATP. It's false. They don't, but these ones do. Okay, and just remember that rule about primary, secondary. I'm going to move on. We're going to have some data analysis. All right, so this slide, I already mentioned this point. With reabsorption and secretion, you can kind of max out. You have transport maximums. So let me erase this. But know what I say after that. Filtration, no max. You can just filter. If it makes it through the filter, it doesn't matter how much is going through. It all goes through. But secretion reabsorption, you can max those processes out. So I wrote that before. I did not write this. So filtration, the function of filtration, we know that occurs at the glomerulus. As though transport max. In other words, you start filtering. If you're measuring the level, if it makes it through the filter and you just increase the level in the blood, it just keeps going. It will never level off. If the level in the blood goes up and it can go through the filter, it all goes through. But what I said prior is that secretion reabsorption can max it out. So for example, reabsorption has the TM, like I see on the slide, transport maximum. So it's like you can increase to a point, but eventually you're going to top off. That's what I'm talking about. You max out at some point. And once you max out, it's just going to remain in the filtrate, and then you probably lose it to the urine. And that's what's shown here, saturation. Saturation refers to this transport mass. All the carriers are used, and they're at their max capacity in terms of operating. So saturation on my little line on the board here. Saturation, to define it, it's a maximum rate of transport for reabsorption. A max rate of transport. So if you look at the units, you're transporting at a rate. Right here. They say on this slide, mgs per minute. You're transporting some physical weight of molecule per unit time. Okay, that's a rate of transport. So example, mgs per minute, rate of transport. The other thing I define is renal threshold. This is the point at which you excrete something into the urine. And the way we monitor it is, look at the plasma concentration in the blood. The renal threshold is the plasma concentration at which you begin to, plasma concentration at which a substrate reaches saturation. Plasma concentration. saturation occurs, it's the threshold at which you begin to excrete something into the urine. It's the threshold at which a substance, and let's use glucose as an example, is excreted into the blood, excreted into the urine. Oh my gosh. Let's get that straight. So threshold is important. It's a concentrated. Blood sugar is too high. You can't reabsorb it all. We have sweet urine. And that's kind of shown here. And so let's make sense of these data slides. And so I kind of color-coded it, and I put the function here so you can kind of see. Here's filtration at the glomerulus. Here's reabsorption, say for example at the PCT. But here's the collecting duct, which monitors excretion. And if you consider the plasma concentration of glucose, if you're within a normal range, you'll reabsorb all of it, and nothing will be excreted. However, if you reach some renal threshold, you'll saturate and begin to excrete. So kind of helps to draw this out. So here's my glomerulus. It's my afferent. It's my efferent. Afferent things are going in. Efferent things are going out. And here's my Bowman's capsule. Is going to catch everything. And let's simplify the nephron as to this simple straight tube here. And the idea of reabsorption, that you're going to reabsorb into a peritubular capillary that's in the vicinity. And let's say you have a normal level of glucose. Let's say these three green dots represent a low value like, I don't know, 100 mg per deciliter. And they all get filtered. They make it through the filter, so they're going to kind of make it into the tubular pole, and they'll all pass by the blood and through the cells. And the transporters for glucose can effectively remove all of the glucose from the filtrate. But as you start to increase your sugar level, let's say 200, so I'll just double it. And you just keep on going, because filtration has no maximum. It keeps getting all filtered. And as long as you're sub-max, you haven't reached saturation yet, you just keep removing it all. And so for these first two concentrations, you see 0 in the collecting duct. There should be no sugar in the urine. However, if you reach threshold, say for example 300, you just keep on going. You're still at the point where you're getting it all, but this is the threshold. This is standing on the edge of a cliff you're about to step over. One more step over, one more tick, and you'll see sugar in the urine. So I mean, if you just kind of just keep on going, I mean, 300, that's saturation, that's AT. So if you go to 400, I think you get the idea. This is too much sugar to be reabsorbed. And that's the point at which you'll start to excrete sugar because you've maxed out your transporters. Okay, so usually this visual students get, it's like, okay, I don't like looking at graphs, but I understand that the 3 dots means you're starting to excrete glucose in the urine. Now, but let's try to make sense of this figure, the third one. They point to the very bottom. That's the point at which you begin to excrete. And that's the point I'm trying to make, you know. So that if you overlap all 3, you can kind of see how they make sense. The red dotted line, it never levels off. Why? There's no match for that function. But the green line, yeah, that's transport maximum. And once you max out, that's when you start to excrete. So that's all I'm going with there. Is there any questions on those data slides?
When it maxes out and it starts excreting, is it still transporting over?
Yeah, they're all transporting at their maximum rate until you stop shoving muffins down your throat. Or downing grape juice or whatever it is that's causing your blood sugar to get so high. I took my son in for see if he had glucose in his urine, and he did. But he shoved a big old Costco chocolate muffin right before I took him. So I don't give a lot of credence to it, so I'll have to take him again. Okay. When the blood plasma concentration of a substance like glucose is so high, it's filtered by the glomerulus, all of it cannot be reabsorbed. So again, that's the leftovers that you're excreting. So the plasma concentration at which you begin to spill, that's the threshold. Okay, so for example, look at this. What was the threshold that we used? What was the number? It was the 300 one. How would you answer this? You know where to look. It's right in front of you. Bam. That's transport max. Remember what we said. Transport max is you move stuff per unit time. That's why it must be one of these choices. A, B, and C cannot be correct because, well, what's the wrong units? This is 1, 2, and 3, A, B, and C. That's kind of referring to like these plasma glucose. I mean, renal threshold is kind of used for that, right? But transport maximum is per unit time. How would you answer this one before we move on? What's being, quote unquote, used up in saturation? What's saturated? What's students commonly say glucose. I'm going for this one. When you're saturated, you got too much glucose because the transporters can't transport it fast enough. So I think in terms of what's being used up, that's what we're going for there. When you max out, too much glucose, but what's being maxed out is the glucose transporter. Okay, so think of it that way. All right, well, let's move on to a different topic altogether. This is no more questions. Okay, acid-base balance. This is shifting gears a little bit. This is actually in a different chapter. But I decided instead of teaching the entire chapter, I'll just take what I want from that chapter and turn it into this chapter, and this is unit, to make it more efficient. Because it, acid-base balance, I think it's the next one, but you know what, let me check to be sure. I used to have the chapter numbers memorized. I think it's 26. Yeah, 26. Urinary system 25. 26. So look what I have on the board there. And look at the figure here. Are you reabsorbing bicarb? Are you excreting, hydrogen ions or protons? Usually it's number 3. You do both of those at the same time. And if you were to do that, you would very effectively combat acidosis. So let's kind of get into this here. All right, so let's talk about bicarbonate. Acid-base balances. That's our bicarb. That's the most useful base buffer for the blood. It's a buffer because, well, it can kind of sop up a hydrogen ion to prevent large changes in blood pH. A buffer doesn't prevent a change, it just kind of keeps the change from being too exaggerated one way or the other. Right, so let's say 100% is 4320 right there. You've reabsorbed most of it at the end of PCT, and you reabsorb most of your bicarb. So 99.9% of it is reabsorbed. So let's look at figures that talk about this. Look what's happening here. You're going to take a molecule, you're going to basically bust it into different pieces, and you're going to transport bicarb one way, and you're going to get rid of an ammonium ion out here. So let's kind of break this down. This is occurring in the PCT. There's an amino acid, glutamine. They say deaminate, oxidation, acidification. Okay, think of one thing. Amino acids, this group an amino group, if you stick a hydrogen ion onto it, think of it that way. We call that NH4+, ammonium ion. In terms of acid-base balance, hydrogen ions or protons, they must be buffered by other molecules because they're too small to be excreted by themselves. I'll just say they must be buffered by other molecules. They're too small to be excreted by themselves. I won't write that, but ammonia buffers. This is kind of what we're talking about here. From the amino acid glutamine, you just break it up into pieces. You acidify the ammonia group to an ammonium ion. This can be excreted. That excretion is coupled with bicarbonate reabsorption. In other words, it's put into the blood. And notice on the figure, they put the word "u" under here. That's significant because in acid-base balance, it's all about how much base is in the blood, how much hydrogen ions are in the blood. That determines pH. Okay. So if the kidney is getting rid of an H+, at the same time adding back a bicarb, it's considered new if they're coupled. They happen at the same time. So this is really effective at combating or compensating for acidosis. Number 1, do that. Number 2, do that. Effective at effective in compensating. For acidosis, right? For whatever reason, blood's getting too acidic. Well, anyways, PCT cells can do that. Let's move on to another buffer system. This is the phosphate buffer system. So just pay attention to the filtrate into the over here. Just kind of. So I'm writing phosphate buffers. So you got HPO4, 2 negative. That's called monohydrogen phosphate. But if you stick a hydrogen ion on it, it becomes H2PO4 negative sign, dihydrogen phosphate. Okay, that's the molecule that's excreted. And at the same time, you've coupled it with a new bicarb that's been reabsorbed. So same thing, it's just this different buffer. It's effective in compensating for acidosis. A third buffer system that's a little more confusing, shown here, is the bicarbonate buffer system. So whenever I teach from a busy slide like this, I always try to tell students, just look at one place to start. And I think you should look at number 6. They don't need to look at number 1. Let's look at actually number 6 first. I think that's where it begins in my mind's eye. That's CO2. It's passing into the cell, and there's no transporter for it. CO2 is an inert gas and it's right through the cell membrane. So let's start there first. Bicarbonate buffer systems. And there's something you're familiar with, the CA, remember that for the respiratory lecture? You hydrate the CO2. Now that's a reversible reaction. It's sped up by carbonic anhydrase. This same equation again. It's some of the metabolism for this cell. And look what they're doing. You reabsorb the bicarb and you excrete the proton. And the proton is buffered by bicarb in the filtrate. So this, reabsorb this, secreted. I say secreted, not excreted. Okay, it's secreted, but if you kind of look, follow the fate of this H+, in the filtrate. It goes H plus plus HCO3 minus H. It just goes in reverse. Okay, so follow this H to here. And where does this H, where does it disappear to? It's in water. Now, most of water is reabsorbed. Think of water as a hidden proton, a hidden hydrogen ion. It's like H plus OH. Think of it that way. And you're not excreting water, you actually reabsorb most of the water. Okay? So water is reabsorbed mostly. So you're not doing that coupled excretion of the proton with the reabsorption of the bicarb. So it's not as effective as compensating for acidosis. I'm not even going to write it because it really doesn't compensate for it. You're just replenishing your base. Okay. So they make a point of not writing the word new, but it's not real apparent that it's not new. That's something. See how they write new, and then they write new. New. Where's the new? It's not new. And so they should make that point a little less subtle. And the other thing we say about this, the reabsorption of the bicarbonate, it's not direct. It's indirect. You write that on the board. Indirect reabsorption of bicarb. So what's meant by indirect? If it were direct, you would take this bicarbonate, and this molecule would be physically moved into the blood, but that is not what happens. Where did I start? What actually enters the cell? CO2. But then through CO2 you do chemistry, and then that bicarbonate is reabsorbed. So that's what's meant by indirect. So that's kind of answering the first question on this next slide. So this other one, what was the buffer used for the metabolism of glutamine? Remember? Not phosphate, amino. Yeah, so don't confuse your different buffers. There's the bicarbonate thing, there's the phosphates, but there's also the amino groups too. This is a good place to take a break. When we come back, we'll do the loop 10. We'll come back at 9:20.